Coming up on Dr. Kiki's Science Hour, we're talking about Hubble. 20 years of Hubble, no less, with Dr. Frank Summers. That's up next on Dr. Kiki's Science Hour.
Netcasts you love.
From people you trust.
This is Twit. Bandwidth for Dr. Kiki's Science Hour is provided by Cachefly at CACHEFLY.com.
This is Dr. Kiki's Science Hour with Dr. Kiki, episode 77, recorded on Thursday, December 16th, 2010. 20 years of Hubble. This episode of Dr. Kiki's Science Hour is brought to you by MailRoute. Visit mailroute.info for a 10% discount. Welcome, everyone, to Dr. Kiki's Science Hour. I'm Dr. Kiki. This is episode 77 of the show that you know gets down and dirty into the science. We spend a whole hour talking about a single topic, usually with an expert in the field, for that entire time. And I enjoy it a lot. I hope you enjoy it somewhat. No, I hope you enjoy it a lot as well. And today, I am so excited to bring you 20 years of Hubble. That's right. This year is the Hubble Space Telescope's 20th anniversary. Hubble has been taking pictures during that time period that have shown us the universe and given us a new appreciation of where we live, who we are, where we might go in the future, what we might explore, and what we still have yet to learn. With me today to talk about the Hubble Space Telescope and the work that he's doing at the Space Telescope, the Hubble Space Telescope Science Institute, is Dr. Frank Summers. And Dr. Summers has a wonderful history. He has been working at the Space Telescope Science Institute bringing astronomy discoveries to the public. He does a podcast for STCI that called Hubble's Universe. Hubble's Universe is a wonderful podcast, video podcast, that shows beautiful images and visualizations from the Hubble Space Telescope, described very eloquently and entertainingly by Dr. Summers. Frank Summers got his start at the... Let's see, where did you start? You got your start. It's not in this part. This background thing that I wrote. There we go. Your PhD. You got your PhD at the University of California in Berkeley. Performed research at Princeton and Columbia universities, and you focused on computer simulations of galaxies and the universe. Took a step away from research and moved into public communication. So we're really lucky to have somebody who is an experienced astrophysicist, computer visualization expert, to talk with us today about all the wonders that the Hubble telescope has been bringing to us. And additionally, he does Taekwondo. He has a brown belt. I have a black belt. We should spar.
No problem. Well, I think with your current condition, I wouldn't really want to spar with you.
Yeah, maybe we'll have to wait. So tell me, Frank, what got you interested in working at the Space Science Institute?
It's the Space
Telescope Science Institute.
Okay, well, as you said, I was in New York City, and I was working at the American Museum of Natural History.
Yeah.
Myself, Neil Tyson, and Steve Soder, we were the three curators that built the New Hayden Planetarium that opened in 2000.
Yeah.
So I was at AMNH for 5 years, and when we finished it, it was an incredible project, and there was a ton more stuff that we wanted to do at AMNH. But really, it was a personal decision for wanting to come to Baltimore to move out of New York City and move back to suburbia. So I could have done amazing research and outreach at AMNH, but another place that I could do really amazing research was with Hubble here at Space Telescope, and being in suburbia really appealed to my wife and I. I really have to say that, I only applied to one place. All right. I said, look, I'm either going to go to Hubble or I'm going to stay in New York. And when I got the job offer from Hubble, it was too good to pass up.
I'm sure it must be just an absolute dream to work on on a project or with a project like the Hubble Space Telescope, the images that come back, the science that you get to describe to people. I mean, how does that feel as somebody who's gone from doing the science to somebody who now communicates the science?
Well, there is something of a feeling of, that we're seeing history in the making around this building. I'm sure when this started out, that it wasn't quite the same because, you weren't sure the telescope was going to work and how much it was going to do. But now that we are, I arrived in 2001, and so that's 11 years into Hubble, and we already knew that Hubble was making discoveries that no other telescope in history has made, and it was making discoveries at a rate that, ranked it up there among some of the most important telescopes in history. I mean, you could really argue that this is the most important telescope in history. So there is a feeling that, when you're in this building, you're watching history in the making. And so when we sit around in our news meetings and we're discussing the latest results from astronomers and saying, all right, now which are the most important results that we want to get out to the public, you're really looking at some of the really cutting edge. And so it's a real pleasure. It's really an honor to be able to participate in this. It's quite a rush. I really do enjoy coming to work every day.
It's good to have a job that you love. So let's start talking about Hubble and the history of this amazing tool that has allowed us to see so much of the universe. Can you give us a kind of an overview of where it started? I guess the seed that Hubble sprung from.
Right. Yeah. The history of Hubble is pretty long. As early as the early 1900s, before while we were still imagining space travel, just after the Jules Verne era, people could imagine putting telescopes in space. I believe there was a paper in 1923 that discussed, in a realistic sense, the possibility of putting a telescope in space. But the first serious white paper was done by Lyman Spitzer for the Rand Corporation in 1946. And this was, a serious paper saying, look, here are the advantages of getting a telescope up above Earth's atmosphere. And of course, the advantages are that you get up above the blurring effects of Earth's atmosphere. It'll have the best resolution of any telescope. And you can also see wavelengths that are absorbed by Earth's atmosphere, the ultraviolet and infrared wavelengths. So it was 1946 when the first serious discussion started arising, and you got to recognize that was, 11 years before Sputnik was launched. Sputnik didn't go up until 1957. NASA arose in 1958. And so the space era didn't really begin until about over a decade after this. And in 1962, very quickly into the space age, the National Academy of Sciences, they recommended that we seriously look at the idea of putting a large telescope in space. Proposals, however, didn't really start until the end of the decade, around 1969. And then, of course, there are all sorts of various competing proposals. Everybody has their idea of what type of telescope it should be, what instruments should be put on it, how you're trying to support it, where you're going to do all the research for it. And it wasn't until 1976 when NASA and ESA, the European Space Agency, combined forces and put together a joint proposal that there was enough political force behind the proposal that it got funded. U.S. Congress funded it in 1977. The Space Telescope Science Institute here in Baltimore was established in 1981. And in 1985, Hubble was ready to be launched. Hubble had been built. Unfortunately, in 1986, we had the Challenger accident. And so the Space Shuttle Challenger accident caused the Space Shuttle fleet to be grounded. So we had to wait until 1990 before the Hubble Space Telescope launched. You can really see it was a long time coming. If you start from 1946 through 1990, that's 44 years of anticipation and waiting for a large space telescope to get launched.
Yeah, and now we have other space telescopes like the James Webb Telescope that we're waiting for, and some others that the period of time for getting some of these telescopes into the air, or I guess into space, has shortened. When I think Hubble maybe did Hubble really set a precedent for our ability to get stuff out there and to do good science visualization research?
Well, the main thing that Hubble did was there had been telescopes in space before Hubble. Okay, Hubble was not the first space telescope.
Right.
What Hubble was the first general purpose space observatory. The missions that had gone before Hubble were specific purpose missions. There were some X-ray missions. There were some infrared missions. There were ultraviolet missions, things to launch an individual satellite up above Earth's atmosphere, get a specific set of observations for a short period of time, and then the satellite would generally not be useful after that. What Hubble was a large optical telescope that could be used for many different purposes. Hubble wasn't designed just to do, planetary astronomy or just to do cosmology. It was designed to do a whole broad spectrum of astronomy. And so it was what we call the first of NASA's great observatories. And it really did establish a precedent for just how much science can be done with a general purpose observatory in space.
And we're reaping the benefits of it still. What do you think it is? I mean, we'll look at the images in just a minute, but I guess the human interest in Hubble. Hubble is beloved. The images that come back from Hubble, people are entranced by them. There was talk of shelving Hubble, of letting it go to, letting it die, not fixing it. But we've scheduled missions to repair it. We've scheduled missions that would allow Hubble to exceed the lifespan that we originally set for it. Why have we gone through all this trouble?
Well, I got to echo something that you said, that the public really has an attachment to Hubble. I have on my computer, I'm always following the Hubble tag on Twitter. And just the number of people who are always constantly, daily streaming about, oh, wow, this incredible Hubble image or that incredible Hubble discovery, it really is impressive. And I think that probably is due to the fact that there's been some drama related with Hubble. I mean, as we all remember, in 1990, when it was launched, the mirror was ground to a very exact shape, but it was just slightly wrong.
Right.
It wasn't in perfect shape, and the public following that drama of, all right, we have a problem, and then the astronauts going up in 1993 and putting in the eyeglasses and being able to repair it, that really got the public, to know about it. I mean, really, seriously, how many scientific instruments can the public name? All right, how many people would know
Hardly
the LA
any.
said it, right?
Yeah.
The Large Hadron Collider, maybe a couple of people would know Fermilab, but Hubble is a household name, partly because of the drama, and then, of course, partly because of the amazing images. Once it was repaired, it has just such incredible resolution that the images just really speak to you. So I think I really find it amazing as a scientist to think that, the public has a emotional attachment to a scientific instrument.
Yeah, I think the story has been told very well. The tale of Hubble, the struggles, the challenges it's faced, the success that it's reaped. It's, there's maybe there are some very basic story threads there that tug at the human heartstring, that allow people to really become connected to a tool, a scientific instrument that's hanging out in space.
And you mentioned the servicing missions. Yeah. Hubble is in what we call low Earth orbit. So it's really just up above Earth's atmosphere.
Yeah.
As you probably know, Earth's atmosphere extends for about 100 kilometers above the surface of Earth. Well, Hubble's only 600 kilometers up. So it's just above Earth's atmosphere. And that means it's serviceable by the space shuttle. Now, as an astronomer who wasn't with Hubble at the time, I was thinking, wow, if we could get Hubble way away from Earth, all that shining from the Earth, and Earth won't block half your orbit, you get away from all the problems that would be associated with being in Earth orbit, would be better. Why are we doing this in low Earth orbit? Well, fortunately, I was dead wrong. The servicing missions have really made Hubble a long-lasting instrument, because I always make the analogy that it's like your computer, okay? I got a computer that was like a 286 All right, and a few years later, I pulled out the motherboard, put in a 486, and I swapped out that old CD-ROM drive and put in a bigger, faster CD-ROM drive, and pulled out that what was it, a 20 megabyte hard drive, and put in a 200 megabyte hard drive, and I felt like I had a brand new computer. The chassis of the computer stayed the same. I just changed out the components, and everything felt like I had a brand new computer. Well, that's exactly what we get to do with Hubble. By going up on these servicing missions, the barrel of the telescope and the mirror, they all stay the same. That's the basics of it. But we're able to pull out the old instrument, take in brand new technology, put in that new instrument, and as an astronomer, we've got a brand new telescope. It feels like we've got a brand new telescope. I mean, the mirror, we've got telescopes that have mirrors that are 100 years old, and they're still operational. So the basics of the mirror don't need to change. It's all of the digital processing on the back end that observes, that detects the light and gets better detections and wider wavelength coverage. That's what really matters in terms of improving the telescope, and that's what we've been able to do with 5 servicing missions. We had mission 1 in '93, 2 in '97, 3A in '99, 3B in 2002. And then, of course, servicing mission 4 in 2009. So that's really been a great help to keeping Hubble at the forefront of science.
Yeah, the ability to be able to service it and to make those improvements has, made it possible to keep up with the advances in technology, to also fix the problems that, the engineering problems that needed to be troubleshot in the beginning. So let's start looking back at the history of Hubble and what images Hubble has given to us over the years. You've compiled a wonderful short list of images for us that I'd like to go through. So I'm just going to put them up on the screen, and then if you can describe them and tell us a little bit about each of these images, I'd love that. So here's the first, 1990.
1990. Now this shows you that even with the flaw in the mirror, Hubble was better than any ground-based telescope. So what you see is on the left, you see a ground-based image of a double star. Okay, and you can't resolve the double star because we're looking through the atmosphere, and twinkle twinkle little star. The atmosphere blurs the stars around. But on the right, we see the Hubble image of that same double star. Even with the flaw in the mirror, it's clearly resolved. And I do this. I love showing this image just to remind people that just getting up above Earth's atmosphere, even if there was the flaw in the mirror, Hubble still had better resolution than any ground-based telescope and still could do science that could not be done from the ground.
Okay. And then we move into 92 being the next image.
All right. Now, this is a wonderful image of the center of a giant elliptical galaxy. These giant elliptical galaxies can have hundreds of billions, even trillions of stars. And at the very core, they have what's called a supermassive black hole. All right, and this is a black hole with perhaps 1 billion times the mass of our sun. And these black holes can sometimes have incredibly energetic emissions. And so what you see emanating off to the left is a jet of emission from the supermassive black hole right at the core of M87. And with Hubble's resolution, we're able to see that in greater detail than we'd ever seen it before. And so we're able to see this incredible energy of these protons and electrons and the high energy particles being spewed out of the region around a supermassive black hole.
Is this some of the first visual evidence that we had of these jets emanating from black holes? I know that they were theorized to exist, but is this kind of when we started going, yeah, we see it, we have evidence?
We did know of the jet in M87 before Hubble was launched, but we couldn't see it as clearly as we could. So really what Hubble was able to do is give us finer detail, finer structure in the jet of M87.
Okay. So the next image that we have is from 1994.
1994. Now, this was a serendipitous observation because fortunately we repaired Hubble in 1993, and then also in 1993, we discovered a comet orbiting around Jupiter that had broken up into 20 or 30 pieces. It's called Shoemaker-Levy 9. And when we computed the orbit for SL9, we figured out it was going to smash into Jupiter. Now, you got to think about this, okay? Put on your thinking caps here, guys. Jupiter is 140,000 kilometers across. These comet pieces are like 2 kilometers across. 140,000 versus 2, right? So what's going to happen? This is a pinprick. Is anything going to happen? All right, but we didn't really know. So when these comet pieces hit Jupiter, all the telescopes in the world were watching, including Hubble. And on the left side, you can see the image of Jupiter in visible light after a number of these comet pieces is hit. And down in the bottom of the image, there are these black marks. These are the places where the comet pieces impacted Jupiter's atmosphere and basically vaporized themselves into these huge explosions. And the other thing about being above Earth's atmosphere is that you can see ultraviolet light. And the right-hand image is a view of Jupiter in ultraviolet light, and you can see that the explosions look much bigger. That's just because you're seeing a different way of looking at Jupiter, and you're seeing deeper into the atmosphere and being able to see the full extent of them. I also want to note that halfway towards the top, there's a very small circular spot in the ultraviolet image. That's not an impact site. That's actually one of Jupiter's moons just casting a shadow on Jupiter.
Okay, so the shadow is a cooler spot, or would it be a cooler spot on the surface? Or hotter?
It's the shadow of
just a shadow.
The shadow of it, so I guess it would be cooler. It wouldn't be emitting ultraviolet light because the moon is blocking it. The moon doesn't emit much ultraviolet light.
Right. I was just comparing the two images, and just you can't see the shadow in the.
Yeah, the two images weren't taken at the same time.
Got it.
Hubble took the visible light image, and then about an hour or so later, it took the ultraviolet image, if I remember correctly.
Okay. So we have another image from 1994, another comparison. This is beautiful.
Right. This one was released actually at the beginning of 1994, and this shows you that the repair worked. Okay. On the left-hand side, you've got the core of the galaxy M100 as viewed through the first camera on Hubble, Wide Field Planetary Camera 1. On the right-hand side, you've got the exact same view, but with the repaired instrument, Wide Field Planetary Camera 2. And this shows you that the astronauts and the engineers did their job superbly.
Yeah.
The right-hand side, that's the resolution we were looking for, and that's when this is, sometimes I call it the most important picture ever, because it shows you that Hubble can achieve what it was designed to do, and this enables all the science that has come thereafter.
Yeah, it makes you think a little bit for a second of what if it had been, the mirror had been right from the beginning, how many more accurate images could have been taken.
Well, we would have had about 3 years more of that, because it was from April 1990 through the servicing mission, which I guess was late 1993, that we got good images. As I said, showed you before, we got better images than them from the ground, but not quite as clear as we really wanted.
Okay, so moving on from the most important picture ever taken, we have an amazingly beautiful image that I think many people will find very familiar.
Yes, this is the famous Pillars of Creation in the Eagle Nebula. And a lot of people look at this image and are just awestruck by it. But I really want you to understand that what's going on here is that there are two major things that are going on here. One is that these pillars are being created by this huge stellar winds, stars that are newborn stars that are blowing out these huge winds that are streaming down across the gas in this nebula. And that's what's creating these pillars. There are dense regions at the tops of these pillars that sort of serve to shadow the regions behind them, and that is what creates these pillars. So it's not like an erosion. It's really like an erosion process when you think of, you know, the pillars in Monument Valley, how they eroded away. You would get you get these long, tall things. All right, and so you've got this erosion process creating them. But then at the very top of those pillars, there are these really small little fingers, and these are places where stars are being born. These are the dense regions in the Eagle Nebula where there are tiny little regions where individual stars are being formed. All right? And so you are seeing really pillars of creation, because this is the creation of the stars. Right in there, those little fingers, each one of those is a new solar system in the process of formation.
It's amazing. And it has to be those areas have to be there. They look, you talk about erosion. They look like they're pillars, like they're not moving, they're not doing much, but these are really dynamic places in the universe, and they really are creating so much. I mean, if you're creating new stars, you're getting new elements, you're getting life-forming molecules, possibly. There's the potential for just so much activity in this image.
All right. I mean, this is where gravity is collapsing the gas to form the stars, but you've also got the radiation and the winds from these stars streaming past. You've got the energy being given off by the newborn stars. You've got the disk of material around the newborn stars where planets might be forming. There's a hotbed of activity going on here.
Absolutely. Okay, so here is an image from 1996. It's another very dynamic image. Oops, hit the wrong button. Let's get the right one up here.
Ah, yes. This is a star that's going to die. Okay, I just showed you stars that were just being born. This is a star on its way to die. It's called Eta Carina, and it's right at the core of this. All right, and in 1840 there was a huge outburst from Eta Carina, and we believe it might have caused a huge blowout of gas from the star. All right, a blowout that created these lobes on either side of the star. So you've got that lobe to the bottom left and a lobe to the upper right, and these have blown out from the star as it's an outburst, which we believe is in the process before the star will die. Eta Carina is a star that's about 100 times the mass of our sun, and we believe that sometime in the next few million years, it's going to explode. It's going to go off as a supernova explosion. So these are, the dying throes, the throes before the death of the star.
Yeah. For the image, do you have any idea, or have you worked on visualizing the gravitational or magnetic forces that are at work to create the shapes that we're looking at? The fact that it's blowing out in such a polar nature with kind of very few emanations that seem to be coming from the sides, or is this just our angle of incidence and how we seem to be looking at the image?
Now, that's a really great point. Something that we astronomers sort of take for granted, but forget to mention sometimes. So when there is a disk of material around the star, okay, and you've got magnetic fields especially, that can tend to produce bipolar jets, okay, especially with young stars, and there are some images later that'll illustrate this. Young stars tend to produce these long, thin jets, all right, that go out in both directions. Just sort of like the jet we saw in M87, right?
Right.
And so we believe there is a disk of material around Eta Car, all right, that is stopping any outflow in the plane of the disk.
Huh,
and so it's forced to go out on these big bubbles that sort of look like an hourglass shape to Eta Car.
Interesting. So there's definitely the mass of the or the forces that are involved in the plane of the solar disk, the solar system that's around it are changing the way that it's able to outburst.
Exactly.
in its dying throes.
That's exactly it, because when you have pressure is going to go take the easiest route out. If there's a lot of stuff stopping it here, it's going to stream out in that direction. That's just basic chemistry.
Yeah. Okay, so here is another image. We have an image from 1998 now, moving ahead a couple of years.
Okay. All right. This is an image of Saturn. You may recognize it, but it probably doesn't look like a normal image of Saturn because it isn't a normal image of Saturn. In 1997, we had a servicing mission 2, and we put on the Space Telescope Imaging Spectrograph. And one of the special things about that instrument was its ultraviolet sensitivity. And so this image here illustrates some of the ultraviolet sensitivity that STIS had by looking at Saturn. And if you look at the bottom of Saturn and the top of Saturn, you can see that there are aurora on Saturn. Just like we have the aurora borealis and the aurora australis on Earth, where charged particles from the sun stream in and hit Earth's atmosphere. Well, the solar wind extends all the way out to Saturn, and those same charged particles hit Saturn's poles and create aurora. However, Saturn is about 10 times further away from the sun than Earth, and so the solar wind would be 1/100th its density at that point as at Earth. So we weren't really expecting there to be a huge amount of auroral activity, and if it was, we expected it to be relatively constant. Well, actually, both of those things were wrong. It was very strong auroral activity, and it was very changeable. It changed on the matter of hours to days rather than days to weeks as we had previously suspected.
Was there any? We're looking at the images, but are there any explanations that people have come up with to explain why the auroral activity is so vibrant?
Yes, there are, but I honestly don't remember them right now. I remember reading up on this a year or two ago, and that the interaction of Saturn's magnetic field with the solar wind was there was a stronger interaction with it, and the other thing is that the rings of Saturn were thought that they were going to interfere a lot with it, and that they didn't interfere as much as we had previously suspected. But that's only half an answer. I'd have to come back to the full answer.
Yeah, well, we'll have to have you back on for sure. Here is another image. We're closing in on the end of the decade, I guess the end of the century, coming into these next two images. 1999.
Yeah. This image I threw in because it's a gorgeous image of a globular star cluster. The sun is a solo star. There are no other stars around for several light years. But some stars live in clusters, and the largest clusters are called globular clusters. They have from 10,000 to 10 million stars in these globular clusters, and they're all orbiting around each other. They're just big swarms of stars. Well, this cluster, Messier 80, has about 50,000 stars, and this is one of the first really great images of a globular cluster that Hubble got. And what Hubble is able to do is that it has such fine resolution, it can resolve stars way down deep into the core of these globular clusters that you could never hope to resolve from the ground. These globular clusters are really dense in the core, and the stars overlap one another. And if you don't have the angular resolution of your telescope, the stars just all blob together, and you can't pick them out. Well, in Messier 80, we can see really down to the core and do really finer detailed studies of the motions of these stars and see what's going on in these intense stellar fields.
Do you have any idea how far apart, what kind of intergalactic distances are between these stars? I mean, out here where we are, stars are so far away from us, or at least other stars seem very far away from us. Are these interacting with each other all the time?
Well, in the solar neighborhood, our nearest star is about 4 light years away. So even traveling at the speed of light, it would take over 4 years to get to the nearest star.
Right.
Inside these globular clusters, the stars are much, much closer together. Let's see, it's about a 1/6 or 1/7 of a parsec. We'll call it about half a light year, okay? So we're down with stars that are, half a light year or even smaller apart.
Wow.
And that's close enough that stars can actually start to interact a lot. Stars are so far apart that generally, they just swoosh past each other and they never collide. They never get caught in each other's gravitational field. Inside the dense cores of globular cluster is the only place in the universe where you will have stellar collisions, stars that will actually collide. And I got to say, this is perfect because you led me on the perfect path, because that's one of the things we discovered in Messier 80. We discovered this incredible type of star called blue stragglers. And these blue stragglers shouldn't be there because the blue stars only live for 50 million, maybe 100 million years. And the stars in Messier 80 are 7, 8, 10 billion years old. So what are these blue stars doing there? And we believe what's happened is that two stars in the core of Messier 80 have collided, merged together, replenished their energy, and now look like a blue star. So you take two yellow stars, combine them together, you get these blue stars. And so there are these host of blue stragglers that we found in Messier 80 that indicate that stars can actually collide inside globular clusters.
Wow. Well, you would expect that if they're at such close distances and they're, affecting each other gravitationally, at some point there are going to be some massive collisions occurring and some big changes. It's a beautiful, beautiful image. Moving more 1999 stuff. We've got a ring nebula up next.
Now, this is we've talked about stellar birth, and we talked about a star that's about to die. This is a star that has already died, okay? Stars live by burning hydrogen in their core into helium, right? The fusion of hydrogen to helium is what powers the sun.
Yeah.
But that's not going to last forever. One day, it's going to run out of hydrogen in its core, all right? And it won't be able to fuse hydrogen into helium. It will move on to become what's called a red giant star, where it fuses helium into carbon. But eventually, that's not going to last forever either. And when it tries to go to move from helium to burning carbon and nitrogen, oxygen, the fusion of those elements, it's not going to have enough mass to press down to create those fusion reactions. And it's going to undergo what we call a helium catastrophe, and it's actually going to blow off its outer layers. So the outer atmosphere of the sun is going to blow off and create a nebula in space. And that's what you're seeing here in this image. This is the outer layers of a star that have blown off into space as it dies, leaving a dense core, a stellar remnant, at its center. So you've basically got a giant ball of carbon, at 50,000 degrees in the core, and then you've got this nebula that's slowly lifted off and is blowing out into space and will eventually cool and fade away. So we can only hope that our sun, when it dies, produces a nebula as beautiful as this one.
Yeah, and is this a true color? Is this added to in any way?
Well, when people ask, all right, is this what your human eye would see? The answer is obviously no. Okay, first of all, Hubble is not an instamatic camera in space, your digital camera in space. It's designed to do scientific observations. So Hubble is designed to see so much more than the human eye could see that, first of all, it's not what the human eye would see. Second of all, the colors are generally especially like these nebular observations, they are narrow wavelength filters trying to find out, all right, what is the oxygen in this nebula doing? What is the silicon? What is the hydrogen? And you look for the specific emissions from the specific elements to give you details of the physics that's going on inside these nebulae.
Right.
Now, hydrogen alpha has a nice pink color, right? And oxygen has a green color. And so we will color these images based upon the wavelengths that they're used to observe it, but they're not taken with the red, green, and blue filters that would produce what the human, an approximation of what the human eye could see if you had eyes as big as Hubble, of course. So we really can't produce exactly what the human eye would see in most of our images. And so we give them colors to make them beautiful, but you shouldn't expect that a scientific instrument is going to give you what the human eye would see.
Okay. I need to take this moment to take a quick break. We're going to take a break between decades as we move from the 90s into a new millennium even, to get a word from our sponsor, MailRoute. This episode of Dr. Kiki Science Hour is brought to you by MailRoute. Businesses of every size use MailRoute. One user to 50,000 users, it really doesn't matter. MailRoute will protect you from spam and viruses, simplify your life, and make your email usable again. People have this complaint all the time. My inbox is full of spam. That email account is to the wolves. you can get it back with MailRoute. MailRoute is a secure hosted service that filters virus and spam for companies of any size. MailRoute can eliminate viruses and spam, reduce the load on your email server, lower your costs, and make your email usable again. Typical MailRoute customers see a 95% reduction in their inbound email volume with virtually no false positives. That's good. We like that. We don't like the errors when the email we like gets deleted or called spam. Leo here at Twit loves MailRoute. He's been using the service for his domains for over 6 years, and it's been his top choice for spam and virus filtering all along. Tom Merritt started using MailRoute, and now he can use email domains that he had given up for dead. Given up as hopeless. There's nothing easier for mail filtering than MailRoute. There's no hardware or software to install. You just sign up with MailRoute and then change the MX records for your domain to start your mail flowing through them. And then they do all the work for you. Makes it nice and easy. Visit mailroute.info to sign up. And as a Twit listener, you'll receive a 10% discount for the lifetime of your account. Small businesses, their accounts start at $2 per user per month for 10 users, and because of demand from the Twit Army, MailRoute has added a new service for individual users as well, less than $30 per year for single users. Visit mailroute.info and sign up with the email filtering service that Tom and Leo use. Thanks, MailRoute, for sponsoring this hour of Dr. Kiki's Science Hour. And now, back to 20 years of Hubble. Hubble is giving us some beautiful, beautiful images, and I'm sure that we have years of images to look forward to. I'm here in the show with Dr. Frank Summers, who is an astrophysicist at the Hubble Space Telescope Science Institute, and he's giving us a tour through some beautiful images from the last 20 years. We're now in the 21st century, year 2001. Dr. Summers, tell us about this image.
One of my favorites. So we've talked about how Hubble has the finest resolution. Okay, well, it's looking here at a cluster of galaxies. Okay, as we talked about stars, they can come in clusters. Well, galaxies can come in large clusters too. And this is a cluster named Abell 2218. It contains thousands of galaxies. So most everything you see in this image is a galaxy, and each of those galaxies contains billions of stars. But the combined mass of this cluster is so large that it actually produces a general relativistic effect. All right, now, I don't know, did you take general relativity when you were in college?
I did not take a specific course on general relativity, no.
Okay.
But well, I am aware of the concept.
Okay. I'm going to tell you everything you need to know about it in 3 words, okay?
Okay, I'm ready.
The words are mass, warps, space.
Yes.
The presence of these huge masses actually warps the fabric of space. That's what you need to know. So when you look at this image, you're seeing lots of very small streaky arcs, these little tiny things that are just sort of streaked and arced, and they all seem to be centered on the center of the cluster. These are gravitationally lensed arcs. What's happening is the mass of the cluster is so immense that the galaxies that are on the far side of the cluster, the light passes through this warped space, and the images of the galaxies become warped out into these long streaky arcs. So light of a normal galaxy comes through warped space, ends up as these gravitationally lensed arcs, and that's what we're seeing in this image. This image is visual proof that general relativity is true, because you can't get gravitational lensing with Newton's theory of gravity. You have to have Einstein's theory of general relativity in order for these gravitational lens arcs to be seen. Now, we saw gravitational lens arcs before Hubble, but Hubble has such great resolution that it has given us the best images ever of the gravitational lensing phenomenon. We can see these arcs closer and closer to the center of clusters than we could ever see before, and so we've learned an immense amount about how much gravitational lensing there is in the universe from Hubble's observations.
That's amazing. That's really fascinating. Okay, moving into the next image, another image from 2001.
Let's back to our planetary stuff. See,
Okay.
one of the things I did with these images is I wanted to show planets and stars and nebulae and galaxies. And you might ask yourself, well, all right, planets, what can Hubble do when we've got, probes that are orbiting around Mars or even landing on Mars and going across its surface? What can Hubble do that these probes can't do?
Yeah.
Well, the fact is that Hubble's up for 20 years. So Hubble can monitor what's going on these planets. And so on the left-hand side of this image, you see a picture of Mars as observed in June 2001. And, it's a fine picture of Mars, but nothing spectacular. But on the right-hand side, you see a picture of Mars in September 2001.
Is that a dust storm?
It's fuzzy, right? And, you might say, oh my gosh, the flaw's back in the mirror. What's going on? No, it's not the flaw back. It is, as you said, this is a global dust storm on Mars. In the left-hand image, in the lower right of that image, that's the Hellas Basin. And there was a localized dust storm starting up over the summer of 2001. And by the fall of 2001, that localized dust storm had gone global. Mars has a very thin atmosphere, so localized disturbances can go global. And Hubble was able to follow this. I sometimes joke that Hubble can sort of be the interplanetary weather channel because it can watch the weather on other planets over the course of years that your more specialized missions usually only have a shorter window of time in which to make their observations.
Speaking about that, does Hubble ever? Where is Hubble directed? Does Hubble ever look at Earth? Do we have that kind of monitoring from Hubble of our own planet?
Hubble does not look at Earth. We have a whole armada of telescopes and other sensing devices that are pointed towards Earth. Hubble doesn't have to look at Earth. And the Earth scientists have, many more satellites that are looking at Earth. So there's plenty plenty of that for Earth. Hubble wasn't designed to look at Earth. It's designed to look out into space. Just to give you a bit more information, Hubble can't look at the sun, of course. It's much too bright. Mm-hmm. Can't look at Mercury because Mercury is too close to the sun, and that would be dangerous for Hubble. But everything outside of Earth, Mercury, and the sun, pretty much fair game.
Okay. So now moving into 2002, we have this beautiful image. It's like ballerinas, but it's not ballerinas.
No, but they are dancing.
Yes.
These are two galaxies locked in each other's gravity and doing a gorgeous dance in which these probably started out as spiral galaxies with great big disks. And as they came into each other's gravitational field, those disks got strung out into these big, long streamers you see extending off to the right and off to the left. We call these tidal tails because they're produced by the tidal forces of gravity. And so you can see the two cores of the galaxies, which will eventually smash together and merge to become one galaxy. And then you also see these big, long tidal tails, which will slowly fall in over billions of years during the dance of two galaxies and their gravitational dance.
The snapshots are just beautiful. It just makes me, being able to see what we can see now. It makes me sad that we can't see into the future to see exactly how the dance is going to end up and where it's going to go.
Well, to do that, we need scientific visualization.
Yes, of which you are an expert.
Yes, and we've done a scientific visualization of this, of two galaxies colliding, and we compare it to Hubble images to show you that, just exactly as you said, each image we get from Hubble is just one frame of a movie that takes 1.5 billion years to play out. So we can do supercomputer simulations that show the whole movie, but Hubble can only, for a given galactic collision, can only get one snapshot of it as it is now. It can, unfortunately, we don't have 1.5 billion years to wait to see how it turns out.
And we can show that image. Let me get it pulled up here. Just 1 second. Back to the beginning. Pause. This visualization is one that's been done of two colliding galaxies.
All right, so here we see the two galaxies in the simulation approaching each other. And at this point, they resemble this Hubble observation, two galaxies just about to come smashing together. And then as the two galaxies come smashing through one another, this collision was set on a nice direct collision. If we rotate that around and look at it from this angle, you can see it matches this Hubble observation of different pairs of a different pair of galaxies. And then you can see really quickly how those tidal tails develop. All right, and then on this Hubble observation, you can see those tidal tails. And then you again turn the time back on in the simulation. The two cores start to come back towards each other. And if you look at this one from a sort of a skew angle along here, we match this Hubble observation of two galaxies. And finally, the two cores come smashing back together, as I said. They merge and will form an individual galaxy. And if you look at it from this, it resembles this train wreck of two galaxies.
Galactic train wreck.
All the while, there's this great big S shape, but it's the time that you view the collision and the angle from which you view it that determines what Hubble sees and when it's viewing galaxy collisions.
Right. For these models, these visualizations, do you go from gravitational principles first, or do you go from images that you've collected? How do you model and then go, oh, look, we have one that looks like that. We have a picture that looks like that, and match it? Or do you say, we have pictures that look like this, let's see if we can make a model that fits?
You actually do both for the research level. For this visualization, this computer simulation was done by Lars Hernquist at Harvard and Chris Mijos at Case Western University. And they did it for research purposes. Okay, that simulation, the results of that simulation have appeared in the pages of the Astrophysical Journal. They gave the data to me to visualize, and then when we had a press release that had 59 images of galaxy collisions, I went through their simulation, and I went through the 59 images, and I said, all right, how many of these can I match to the different stages of the galaxy collisions? And as you see, I was able to match 5 of them. I really didn't expect I'd be able to match 5 different galaxy collision images with one simulation. That was luck. I was really very pleased to be able to illustrate the whole story with one simulation and some images from Hubble.
Yeah, you're just that good. That's what we say. You're just that good. Okay, let's move into 2003. This is another. The images just get more and more striking.
Yeah, and you know what you're noting is that in 2000, that last image and this image are from Hubble's new camera that was put on in 2002, the Advanced Camera for Surveys. And this was a 16 megapixel camera that had much finer sensitivity and larger pixel space. So it really opened up a lot of things. And what you see here is the Sombrero Galaxy. Now, you're used to spiral galaxies probably, right? Galaxies with these great spiral arms.
Yeah.
And then I showed you an elliptical galaxy earlier, which is just a great big ball of stars. Well, this is sort of a cross between them. This has that disk that you see there, but it also has the huge ball of stars for the bulge of it. And so we call this a lenticular galaxy. But the Hubble thing that makes this image special is this is the beginning of we started to do mosaics. This is 6 different pointings of Hubble all combined together. So as I said, the camera was 16 megapixels. Add up all the pixels in this. There's a little bit of overlap. This is a 72 megapixel image from Hubble covering a huge galaxy on the sky. And so this is when we started producing some really, really large images with the Advanced Camera for Surveys.
It's beautiful. And let's move into 2004 from here.
Now this is another most important image ever taken by Hubble, okay? Because this is the Hubble Ultra Deep Field, all right? Now, we talked about distances in astronomy. And you measure distances by light years. And, you know, if a star is 5 light years away, it takes 5 years for that star's light to travel across space before we see it, right?
Yeah.
The galaxies in this image are 5, 6, 7, 8, more than 10 billion light years away. This image, we stared at one spot in the sky for about 1 million seconds. That's about 11 days. And we didn't do it all in one exposure. We took multiple exposures, co-added them together, and we got the deepest image ever taken of the universe. We call it the Hubble Ultra Deep Field. And it shows us the faintest galaxies, the most distant galaxies, and galaxies that we're seeing 10 billion light years away are actually being seen as they were 10 billion years ago.
It's a real eye into the past.
Exactly. That's what great, with astronomy, we can look out into the universe and look back in time, and what you see is the whole history of galaxies. So the nearby galaxies, they're present-day galaxies, and then, halfway out in the universe, these are middle-aged galaxies, and then all the way out the edge of the universe, these are baby galaxies. These are galaxies that are just forming, because the universe is only about 13.7 billion years old. Galaxies formed around 10, 11, 12 billion years ago. We're seeing baby galaxies in this image, all the way through middle-aged galaxies, all the way through adult galaxies. And for someone who did his thesis work on galaxy formation, this is exactly what I would have wanted when I was doing my PhD.
Right.
Pictures to show me what those galaxies look like, because I was just simulating them on the computer. And this picture really shows you what they look like over time.
You can see, and once again, these are colors representing the chemical spectra, representing the what's happening dynamically or in those different galaxies.
Well, in this image, we've got a couple broadband filters, the blue and visible, but we also have infrared filters in this image, because as galaxies are very distant galaxies, their light is redshifted.
Redshift, yeah.
Right, so the light that starts out in visible wavelengths gets stretched due to the expansion of the universe. And by the time we see it, the wavelengths have become long enough to be infrared. So we're using Hubble's infrared filters for some of this image. And so the very reddest parts of this image are objects that are seen only in the infrared. And so if we see in this image a tiny little red dot, that's going to be one of the most distant galaxies in the universe. People want to say, oh, show us the most distant thing you've ever seen, right? It's going to be a tiny little red dot. It's a really important red dot.
Very important, but tiny. Very important, but tiny red dot. Okay, here comes another fun image. These are all fun. I love them.
I'm glad you showed this one, okay? Because we showed you Eta Car early, and we said this is a star that's about to explode sometime in the next million years. This is the Crab Nebula. It's a star that did explode 1,000 years ago. It was observed by Chinese astronomers in 1054 that there was a brilliant star that appeared in the sky. Well, at that same spot in the sky today, we see this image, the Crab Nebula. And the Crab Nebula is basically the guts of the star. I mean, when this star explodes, the whole thing just gets blown into space. All right, this is the guts of the star streaming across the space at 10 million miles an hour. And you can see after 1,000 years, it's reached out to about 7 light years across. So this stuff is really booking across space. And this one, we definitely are looking at this in the different chemical elements. So these are the colors here represent different lines that we're looking at, whether it's nitrogen or oxygen or sulfur. Don't know exactly which lines here. But we're looking at the elements that are blown out of the star in the supernova explosion.
And those elements then go on to seed the universe, right? So the elements that get blown out can go into creating other things within the universe.
Right. The point that you're referring to here is that the place that elements heavier than hydrogen and helium are created are in this cores of stars.
Right.
Because the universe started out as almost entirely hydrogen and helium, just a tiny little smattering of lithium or other things. And so if you're going to create the heavy elements, right, they had to be created in a star, right? And I like to say that I wear a supernova explosion, I wear the remnant of a supernova explosion on my left hand. It's my wedding ring.
A wedding ring.
Every atom of gold in this wedding ring had to be made in a supernova explosion. No other time in the universe do we have enough abundant energy to create elements heavier beyond iron in the periodic table. This is a supernova remnant. You probably have one on your finger, all right? It's just, to think about it, the elements are created in the stars blown out into interstellar space. They're then brought into these nebulae that collapse and form stars. And around one of those stars, planets form, and those elements are part of that planet, and then they become us. It's a fun story to think about.
Yeah, I love that. Okay, we're getting to the end of the show, but I want to get through the rest of these images. They're so great. So I'm gonna try and keep my questions to a minimum.
I'll keep my responses. You can see I can go on and on. There's just such cool stuff here.
It is. It's just amazing. So here's 2005.
This is the Whirlpool Galaxy. This is one of your prototypical spiral galaxies. Actually, the first one ever discovered. And this, again, is a mosaic taken with ACS. It celebrated Hubble's 15th anniversary. And you see all those pink dots in this image? Each one of those pink dots is a star-forming region where thousands upon thousands of stars are forming. And if you look at all of those pink dots, you can start to get the feel that, wow, these galaxies really do contain hundreds of billions of stars. And it's an incredibly detailed image. There's like 100 million pixels in this image. I encourage your viewers to download it and look at all the details because it's just gorgeous.
Yeah, and and then this is only one galaxy, and so you add all of the galaxies and the millions of stars, and it just grows in number and complexity. 2006.
Yes, this is one of the largest images we've ever done. It is a mosaic of the Orion Nebula, one of the nearest star-forming regions. So one of those tiny, tiny little pink dots in that previous image becomes, when you look at it in great detail, a gorgeous nebula like this. In this image and in other images of the Orion Nebula, we've actually seen not just the collapsing of stars, but we've seen the actual disks of material around those stars where planetary systems are forming. We have seen other solar systems in the making in nebulas like this, and it has revolutionized our understanding of how stars and planets form, and they form together as one process.
Yeah, and Hubble has been a huge part of being able to visualize these things, to be able to appreciate and understand them that much better. 2007.
Okay, now this is another star-forming region, but it's at a later stage. All right, and you can see the cluster in the center, that bright blue cluster of stars. Mm-hmm. Those are the newborn stars, and they have gotten so hot that they've blown away the gas of the nebula. In the Orion Nebula, the gas is still there. The stars haven't had enough time to blow away the gas. Those stars are only a couple million years old. These stars are probably 10, maybe 20 million years old. They started to blow away the gas of the nebula. And if you look up top and down bottom, you can start to see those pillars. Remember I showed you the pillars of creation earlier on? Well, those pillars are the same things that we see in the Eagle Nebula, but here we're showing it to you in another star-forming region.
Yeah, it's neat to see everything kind of come together. You start seeing it all work together. It's neat. Jupiter's red spot.
Yes, the great red spot on Jupiter.
It's a storm that's been raging for years, right?
For hundreds of years.
Yeah.
We've had continuous observations of the great red spot since the 1820s, and we may have seen it as early as 1670. Giovanni Cassini has a drawing in one of his papers from 1670 where I swear it looks exactly like the great red spot. We can't confirm that's what it is. But we've never seen any red spots form or any red spots dissipate. The red spot has always been there, so we didn't know much about it. Well, just under the great red spot, we have what we call red spot junior. And red spot junior formed in 2002, 2003, and it was actually the merger of three other storms that formed the red spot. So Hubble was able to watch the first formation of a red spot. And then if you see just to the left of the great red spot is what we call baby red spot. And baby red spot showed up in early 2008. And what you see is that baby red spot is on the same latitude as the great red spot, and it's moving left to right relative to the great red spot. It got caught in the vortex of the great red spot by the end of the summer 2008, and it dissipated away. So Hubble was able to see both the formation of a red spot and the destruction of a red spot. And that's what it gets by being able to monitor these planets for many decades.
Yeah, lots of information, being able to see change over time. Gorgeous.
Absolutely gorgeous. This is one of the first images, what we call the early release observations after servicing mission 4 in 2009. So the astronauts went up and repaired Hubble in May 2009. In September, we released these images. This is another dying star. I showed you a nice bubble of a planetary nebula earlier, the Ring Nebula. This one, again, has one of those disks around the center, and it's just squeezing outflow to go out in bipolar directions. And so the gas is flowing to the bottom right and to the upper left, and as this star is slowly dying. So this is not an explosion. This is a gentle blow off of the outer layers of the star. This one has just started. The star is really, really hot, and so the energy of the gas is being heated up to really high temperatures. So it really is a vibrant view of a dying star.
And moving from a dying star to just an overwhelming image.
This is also from the early release observations after servicing mission 4, and it illustrates the expanded power Hubble has for looking in the ultraviolet and the infrared, because nothing in this image was taken in visible light. The red parts of it were taken in an infrared light, and the blue parts were taken in ultraviolet light. They were taken with the same instrument. So the Wide Field Camera 3 that we put on Hubble in servicing mission 4 has a greater expansion, a wider range of wavelengths that it can observe than previously Hubble has had. And it shows you that Hubble, after servicing mission 4, is the best it's ever been. It is able to do more observations and better observations than it's ever been. It's not a 20-year-old telescope. It really feels, like, as I said before, like a brand new telescope.
That's what a tune-up can do for you.
Exactly.
And 2010, we've seen, this is a beautiful image.
This was our 20th anniversary image.
Yeah.
And we had to find something that would show off the, that would compete with the incredible beauty that we've had before. And I really think they did a great job in choosing this. This is another one of those pillars, all right, like the pillars in the Eagle Nebula I showed you before. But if you look at the very top of that finger sticking out there, you can see those two jets streaming out left and right from that top of that finger, right? That's a newborn star. Those are the jets coming out of the newborn star. In the very top of that finger is a star that has just been born, just turned on, and it's got these jets of material streaming out from either side. So this is another what we call bipolar outflow from a newborn star. And besides the gorgeousness of this image, it illustrates that this is a place where stars really are being born, and you can see concrete evidence of them being born.
It's amazing to be able to see the force from the jets. You can see in the gas. It seems as though in the gases there's it's as if you can see gases getting pushed away at the ends.
Yeah, exactly. At the left end, you can see that curved bow shock. Yeah. That's when the jet is slamming into the gas that exists out in the interstellar space. And so as it hits that interstellar space, it creates a bow shock, just like a boat moving through water would.
It's amazing. Beautiful, beautiful images. Hubble has done some amazing work. So it's 2010, 20th anniversary of Hubble. Where's Hubble going? What are the plans for Hubble in the future?
Well, the space shuttle program is being retired next year, so we can't go up and service Hubble again. All right, servicing mission 4 was the last servicing mission to Hubble, but we did everything, and I mean, the astronauts did an incredible job. They accomplished everything on the to-do list to put Hubble in the best shape it's ever been in. So it's got new batteries, it's got new gyroscopes, it's got new instruments, it's got repaired instruments, and I guess the official word is that it should last for at least 5 years more. But I got to tell you, nobody around here believes that. We believe it's going to last 10 years and maybe even more. You know, Hubble has shown a remarkable hardiness in lasting 20 years. We really hope that we're going to get 30 years and maybe a bit more out of Hubble. So we can expect some great discoveries and some gorgeous images for many years to come.
I'm looking forward to it. Thank you, Dr. Summers, for joining us here today. This has been I'm just enraptured by the images. I'm like anybody. You show me these pretty pictures, and I'm like, wow, This is where we live? How cool. It's kind of nice to have a good view out. It's wonderful, actually, not just kind of nice, but wonderful to have this amazing view out into the universe and to be able to get the kind of information that we're able to get from these images and show us where we need to ask more questions and where we need to move forward in the future. And really looking forward to hearing more. So thank you so much for joining me. Anyone out there who's interested in keeping up with Hubble and the Space Telescope Science Institute, the Hubble site, hubblesite.org, is a website that you can visit whenever you want. It's there on the web. You go visit the website and look, they have holiday sparkle. Those are stars, galaxies. Ah, amazing. Those aren't just Christmas lights, but they work pretty well. A lot of information about Hubble, other space telescopes that are out there, the Webb telescope, and more. Additionally, Hubble's Universe Unfiltered, a video podcast that you can check out at your leisure. Some really interesting information out there talking about information that Hubble is helping us to uncover. So Hubble's Universe Unfiltered, the Hubble site, hubblesite.org. Get more information about Hubble. And that's it for this hour of Dr. Kiki's Science Hour. Thank you once again, Dr. Summers. Really appreciate this. I do hope that we can get you back on sometime. This was great. Maybe we can spar again sometime.
I would really look forward to it. Thank you so much, Dr. Kiki.
Yeah, thank you. Everyone out there, if you'd like to catch more episodes of Dr. Kiki's Science Hour, you can go to twit.tv/Kiki to subscribe. You can also find us on YouTube. Video episodes up on YouTube. So if you missed this and you're listening to this in audio, or if you listen to the whole thing on audio and you're going, where can I find the video? Go to YouTube. We have our videos up there that you can watch. Additionally, next time on this show, we'll be talking about the X Prize with Erica Wagner, X Prize and space travel. So we've gone from the Hubble and looking at the universe to the gift of innovation and how do we make games out of innovation to get people to go places that we've never gone before. Catch that next time. Dr. Kiki's Science Hour is live on the Twit Network every Thursday, 4 to 5 p.m. Pacific time. And I'll be back next week. Thank you for watching this hour. If nothing else, I hope it made your world a whole lot more interesting.